Yeah, okay, like that was what I was trying to write. That was like the short, like I was trying to cheat my way out, reminding the very end of last lecture that we might need later today. But we only started in 1 minute, so I can just explain to Ralph what's a diamond. So this was something that was like, it lives in some flag space, f theta. So this flag space is some sort of boundary in some symmetric space. And what we do is we want to have some sort of subset of this flag manifold that's associated with a pair of points A and B. So I take two transverse points in the flag manifold, and I look at all the other points C that are transverse to both A and B. Right? That's what I'm trying to draw in this schematic. So taking out all the things that are non-transverse to A or non-transverse to B might or not disconnect the flag space in components. And the diamond is a choice of such a connected component. So the choice of A and B disconnect the flag space, possibly in a finite number of connected components. Maybe it's still connected. We have seen an example of that. And for all complex Lie group, it's easy to see that it will still be connected, because I'm cutting out real codimension 2 subspaces that do not disconnect. But there are cases of group G and flag manifolds F theta in which taking 2 points out and everything that's in bad position with them out disconnects in connected components. And then I can choose some of those. And these are diamonds if they are nested. If family of diamonds with good nesting properties, which really meant that if I have A and B 2 diamonds and they determine this and I choose this interval, I choose a point C in this diamond, then I can find, and it will be then unique, other diamonds D prime determined by C and B that's nested and that's inside. We've seen that this is the picture that we see in the circle, and it's a result of Guichard and Wienhard, that this happens in few other cases. So this is a theorem, and this was asked. Someone asked me the list, so here is the list. This is a theorem by Guichard and Wienhard. Saying that a pair GP theta, so a semi-simple Lie group, or simple Lie group. This is for simple Lie groups, and like if I take products, I take products. That's a simple Lie group with respect to a parabolic. So like this gives me a flag space is a theta positive pair, so that I can find this family of diamonds precisely in these 4 cases. The first one is when G is split, if you know what that is. Otherwise, you think of SLNR, for example. That's if you don't know what split is. And then theta is the full set of roots. That's one case. So this is one family. Like there are, we have a question? No. There are like a few of those. Like there are a few classical linear algebraic groups that are split, meaning that the rank as the real rank, using what like the kind of terminology that Natalie was using this morning, is equal to the complex rank of the group. And then this is one case. The second case is when G is Hermitian, which means that the symmetric space admits a complex structure. And one example of this is SUPP. And I want Hermitian of tube type. For whoever knows what that means. Otherwise, you think of SUPP. That's one example. That's in the exercise sheet. And then theta is one single root, which is the long root, whatever that is. In particular, in this example, so the flag space F theta is the maximal isotropic subspaces. And in general, you have, this is the Shilov this flag space in general is the Shilov boundary for whoever knows what that is. And there are 2 more cases. One is the case of the group SOPQ, so preserving a form of signature PQ. And as I was saying before, I always think that P is more or equal than Q for simplicity. And then here there is a theta positive structure, or a family of diamonds, also in the flag corresponding to alpha all the roots but the last one, which is nested isotropic subspaces of all but one less than the rank. Notice that if Q is equal to P minus 1 or P, then I have 2 different structures, because it's also split.
Do you require the one to be more than or equal to 2? Like, can you have P or Q be 1?
Yeah, sorry. Here I want P at least 2. But because otherwise, if P was 1, then I had an empty. So if P was 1, I had the rank 1 group. But then this would not make sense because I have no root. And so it's, yeah. So here P is like 2 smaller or equal than P, smaller than Q. And if P is equal to 2, then I'm Hermitian. So it's, and the notion agrees. Yuzuka, you had also a question or a complaint? No. Okay. And the last family is a set of exceptional Lie groups. I don't know who cares about them. I'm very afraid of exceptional groups, but let me put them here for completeness. These are some real forms of some exceptional group, whatever that is, whose real root system is of type F4, so I have this picture. And the family of diamonds is for the long roots, so half of them.
So you can also get the split exceptional groups in the
yeah, so like for F4, type F4, this is split. And this group has 2 different positive structures, one on this flag manifold and one on the full flag manifold. So there are some groups that admit more than one positive structure with some different parabolics. This is one example. SP2N is another example. Here I have like one flag that admits a family of diamonds, another flag that admits another family of diamonds. Actually, like they are compatible. But you have more representations that are positive with respect to this than for the full flag. Yeah?
Just some like basic one. Like so the logical structure is that if G comma P theta is a positive pair and G is split, then theta is necessarily delta. Is it like that? Or
no, that's not true. Like so like the statement I'm making here is that in all these cases I have a family of diamonds and I have a family of diamonds precisely in these cases. Okay, so there are some split groups that are also somewhere else, and then I can allow different sets of thetas and different family of diamonds and different notions of positivity. Yeah? Yeah?
But does they give us a different collective component, or?
Yeah. So for example, the one that I know that's very close to my heart is SP. The one that I didn't put it up here. So SP2NR. SP2NR is both split and Hermitian. And maybe something that I wanted to mention, maybe a name for those of you who have heard this, then the theta positive representation in the case of split group are called Hitchin representations. And the theta positive representation in the case of groups of Hermitian type are called maximal representations. The others do not have other names. And in SP2NR, that fits in both categories, Hitchin representations are maximal, but there are more maximal representations than Hitchin.
Okay, so is it always the case that if your group is one of the last 3 and is split, then the positive representation with respect to them is also contains a Hitchin representation?
Yes, I think so. I'm not entirely sure for F4, but I think so. And that's and there are more components otherwise. Yeah. And like the history here is that like Hitchin representation and maximal representations came out around 20 years ago. They've been very studied by many people, and the motivation of Olivier and Anna to figure out this theta positivity is to put them in the same framework. And we discovered new other interesting examples. There are these SOPQ and these exceptional groups. Unfortunately, the list is not so long, but still there are lots of interesting phenomena for these representations and many more to be explored. Yeah? More questions or comments? So this is what I promised last time. Now we can start the lecture. So I have 10 minutes less because.
No, you have 10 minutes more.
So we start now and we go 10 minutes long. Okay, very good. Okay, so today I want okay, I didn't finish to write there, but I hope you remember that like I talked about theta positive representations up there. So like we say that rho from gamma, which is always going to be the fundamental group of a surface, into G, if G theta is a theta positive pair, is theta positive if it admits an equivariant positive boundary map that I was calling phi from the boundary of gamma, which is a circle, with its orientation into this f theta. Right? And maybe a theorem that I will not comment at all about, that was supposed to be the end of my last lecture by Guichard-Labourie-Wienhard, is that theta positive representation are Anosov, theta Anosov, and this is the boundary map. So this thing is continuous transverse and dynamics preserving. And that's the boundary map for Anosov representations. And from here, it's not so hard to show that they are, this implies that theta positive representations are open. So the idea is that we know that Anosov representations are open. This means that if I perturb the representation a little bit, I will still get the boundary map. And the extra statement I'm putting here is that the Anosov boundary map for a small perturbation is also going to be positive. This is because the action on triples in the boundary is co-compact. And you understand diamonds well enough to show that this is nice. Yeah? So that nearby maps to positive map are still positive. Yeah? So the plan for my last two lectures is to comment on joint work with Beyrer, Guichard-Labourie, and Wienhard. So the names are already there, so I don't write them again, showing that theta positive representations are closed.
Can you put down the blackboard on that?
Sorry.
Thank you.
So like the goal is to prove a theorem saying that theta positive representations are closed. And thus they form connected components. Of character varieties. This is the theorem joint with Jonas Beyrer and Olivier François and Anna. But more than that, I want to, like, in the way of proving this theorem or telling you some ideas within the proof of this theorem, I want to talk about two geometric features of theta positive representations that make them similar to holonomies of hyperbolic structure. So to action on the universal covering coming from choosing a metric on the surface. So like the Teichmüller theory I started from. Yeah?
Can you just remind me quickly what makes a boundary map positive?
Yeah, so the boundary map is positive, means that for any cyclically oriented that maps positive entuples to positive entuples. So this meant positive entuples in S1 to the n gets mapped to positive entuples in F theta to the n. So the idea here is that I was telling you that I want to think of these diamonds as intervals in the circle, like intervals in the circle are an example of these diamonds. And they let me talk about positivity, like an entuple is positive if I start from, I take the first and the last, and then I want to be able to find, I want A1 to be in one diamond, I want A2 to be in the next diamond, and so on and so forth. So this gives me, I think of this as a notion of cyclic orientation. I mean, non-positive and negative orientation, because like by one of the properties of these diamonds that I had yesterday, I am messing with positive and negative. And there is a good reason for doing so, because there is typically not an invariant way in the flag manifold of telling positive and negative. They're all diamonds, but still this is a way of generalizing cyclically oriented. Yeah.
If gamma is an arbitrary discrete group, is there a way to give a notion of causality on the boundary of gamma to generalize this definition? Like if it's not necessarily a surface group?
So like the only case in which I know how to do this is for subgroups of PSL2R. Then, and this notion works exactly similarly for free groups, for example, in SL2R, or actually for many things that we're going to do today, and also to show closeness in general, you don't need the group to be finitely generated. Any subgroup of PSL2R will have positive representation, and the theory will behave well enough for in this general setting. But like having a cyclic ordering on the group is very restricted.
Excuse me, I probably missed a sentence, but you say that positive representation are Anosov, okay?
Right.
And Anosov are open, but why should it imply that?
Yeah, so this I said and did not write. The idea is that it's not so, it's an exercise to show that the Anosov map, like Anosov representation are open, but they're not just open. The maps vary continuously on the Anosov, the boundary maps vary continuously on the boundary map, on the character variety. And it's not hard to show understanding diamonds a bit and using the co-compactness of the action on triples to persuade yourself that the limit of positive map the limit of positive maps is still positive. The idea is that the limiting map will be transverse because it's part of being Anosov, and then you cannot exit diamonds because diamonds are defined really by being transverse, are correct components of being transverse. Combining these and the co-compactness of the group, you get easily that you deduce. This is an exercise.
And then the Anosov, were they all also connected components, or is
No.
it just an open condition?
This is just an open condition. Okay. And it's very important that there are many, many Anosov representations, and there are there is example in which the character variety is connected. So for example, if you have a joint complex Lie group, the character variety is connected and contains the trivial representation that's definitely non-Anosov, because it's definitely non-injective. And typically you can perturb Anosov representations to get bad, to lose the the domain of discrete and injective, like virtually injective, finite kernel. But these are instead components. And like another example is like in rank 1, Anosov is the same as convex compact. And convex compact is nice, but has a very fractal boundary typically. So it's an open subset whose boundary is very interesting and very difficult. Okay? More questions or comments? So if not, let me tell you like theorem 1. That's what I want to. Let me go towards theorem 1. Today is lecture 3, which is positivity of cross ratios. So this is the first. It will take me a few minutes before I can state it properly, but this is the first geometric property of theta positive representations that we prove, which will eventually lead to closeness. But I find these, in a sense, more interesting than closeness itself. And someone asked me yesterday during the break, in which, like I said, that these theta positive representations are really the generalization of Teichmüller space, as opposed to an Anosov representation that's the generalization of all convex or compact subgroups. And this is going to be one way in which theta positive representations are very similar to hyperbolizations, as opposed to hyperbolic structure on 3 manifolds. Yeah? Okay, and what's the cross ratio? The cross ratio is the classical thing that you might have seen in projective geometry. Like if you've done any course in projective geometry, this is the first thing you see. So like, let me write the formula. So I'll write I'm always debating because I like to write cross ratio, but if you work with François Labourie, you have to write B for B rapport. And maybe since we are at the HS, I should write B, but so I might switch between C, R, and B back and forth in the lecture, because I don't know if my notes are correct. So this is C minus A, D minus B over C minus B, D minus A. So like the idea here is that here is really on the hyperbolic disk. So here I have the disk, and I have 3 points A, B, C, D in the boundary of the disk, and I have one invariant of 4 tuples that are not super degenerate. We can think of them as being all pairwise transverse. I mean, it extends a little bit, but up to the PSL2R action. And this is this unique invariant. Yeah. And why is the cross ratio? Everyone has seen this at some point, or yeah. And why is the cross ratio useful? This is useful because it allows us to compute length. Like if I want to do hyperbolic geometry, I can do hyperbolic geometry on the boundary using the cross ratio and use the cross ratio to compute length. To check that my notations are correct. So if I have, now it's a picture in H2, I have an oxidromic element, gamma, an isometry of H2 that fixes the points gamma minus and the points gamma plus, so attracts everything to gamma plus apart from gamma minus. I choose any point x, and I choose its orbit gamma x. Then we have that the cross ratio of gamma plus, gamma minus, x, and gamma x is e to the hyperbolic length of gamma over 2, where the hyperbolic length is the distance between p and gamma p, between any points, and it's translate on the axis. Yeah, so I can just compute one cross ratio on the boundary and read these are the eigenvalues of like this is the root or the product of the top and bottom eigenvalue, and I guess I shouldn't have this over 2, I think. I think this was the correct one. Yeah? And this is a very useful tool to study hyperbolic geometry because it lets me read lengths of elements or lengths of short curves through understanding boundary. And since I was telling you that I want to do geometry just by looking at boundary maps, is a way in which I can encode in boundary maps properties of the geometric property of the quotient manifolds. All on board? So, and like the important point is that this generalizes to various flag manifolds. And like we take some like in order to state what this positivity of cross ratio means, we choose some specific realization of cross ratios in general flag manifolds. And so like, let me just do an example for you. So if G is SL D R, we consider F1 D minus 1, which are pairs of points and hyperplanes, pairs of a point in R P D minus 1 cross R P D minus 1 dual, and the hyperplane contains the plot point, so P in H. So in SL3 is H point. This is the flag where I want to do this story. And one can write a cross ratio that I'll write P1, P2, H. What do I want? Yeah, P1, P2, H3, H4. So here I want to compute a cross ratio of 4 flags. So I have P1, H1, P2, H2, and I go on, but I only care about the 2 points and the 2 hyperplanes,3, H4. So like only the points of the first 2 are relevant and only the hyperplanes of the other two are relevant. And this is as a formula, which is I compute H3 of P1, H4 of P2 over H3 of P2, H4 of P1. So, and when I'm and here I'm really abusing notation, but the point is that the point I choose one representative in this. So this point is a one-dimensional vector space. I choose one representative in there. I choose a functional that vanishes on H3. I choose a functional that vanishes on A4, and I choose a representative in here. And I compute what the functional does on the point, and I divide. So this gives me a number in R that you can choose is, well, it does not depend on the choice. Of representatives, and is invariant under the PSL dr action. And so this is what I call, maybe I should not put parentheses, I should call like this. CR of this. And again, I have the same thing that if I take gamma plus, gamma minus, x, and gamma x, this is lambda 1 over lambda d of gamma. So where my picture here is that I choose now a matrix in PSLDR, and I call gamma plus the span of the top eigenvalue, and gamma minus the span of the bottom eigenvalue. I'm assuming that elements in here are diagonalizable, or at least have a single one-dimensional top eigenspace and bottom eigenspace, but that it's a general thing. It's always going to be the case for theta Anosov, for theta positive representations. And now, regardless of what hyperplane I take and what image I take, and I compute its image, and I compute this cross ratio, this is also independent on the point that I chose, and always spits out lambda 1 over lambda d. So the idea is that, so here is gamma plus, here is gamma minus, here is x, and here is gamma of x. And for the way these things are set up, the cross ratio between these two hyperplanes and the 2 points is nothing but take the projective line through the 2 points, gamma plus and gamma minus now here. This determines the projective line, and I look at the intersections. And this cross ratio that I wrote up here is nothing but the standard RP1 cross ratio of the 4 points that intersect. So, but again, this is a way that, it's very similar to things that appeared in Natalie's talk this morning of reading, properties of this element gamma of the actional symmetric space from the boundary. And maybe one important remark that might play a role, that will play a role tomorrow, is that this general cross ratio in SLD is nice, but is not as nice as this one, because here I broke the symmetry. 2 are points and 2 are hyperplanes. So I have some symmetry of the cross ratio that involves, like, if I permute, I know what happens, if I permute the first pair or the second pair, but these I cannot exchange because of very different roles. Less symmetries than the cross ratio on the left. Because in here, I have formulas of what happens to this cross ratio for all possible permutations. While here, I can only do these 2 transpositions. And that's the only thing I know how to do. Yeah.
Can you if you take a different cross ratio with hyperplanes in the first two and points in the second two, do you still reach the same length?
Yes. Yeah, that's the same. That's like I could have, if I chose these 2 points and the hyperplane, the repelling hyperplane, it would still be the same cross ratio. Okay, but now we are interested in many more groups, and like I was hoping that at this point I had much more representation theory, but I don't. But so like in for general, so this was an example. Like this was the like maybe like so the this was the RP1 cross ratio. Put an example, the example 2. And in general, like you can do these things for all flag manifolds, and you can get lots and lots of different cross ratios on different flag manifolds. The thing that will be most relevant for my work later, and all these cross ratio let you read different linear combinations of logarithms of eigenvalues of the group elements. And there are various natural ways of defining this. The way that helps us controlling them in the case of interest is to do them through representation theory. So like for a general group, so if I have a general group G, what will be relevant for me is that, and I have theta, a subset of roots, like this. These are a special combination of eigenvalues, or logarithms of eigenvalues, that come from the Lie theory of G. Then for any alpha in theta, we choose a linear representation, pretty much as Natalie was doing this morning, maybe tau from G to SL Rn. Like I choose an action of G on a vector space of dimension n with lambda 1 over lambda 2 of tau of G equal e to the alpha of tau of G. So I want that if I compute the first root in SLD, I get the root that I wanted in theta, in G, when I restrict to the image of the Lie algebra of G.
You need a projective
Yes. Yeah, alpha of lambda, you're right. Thanks. Yeah. No, I mean, I have the ratio of the eigenvalues are e to the alpha of, sorry, that's right, where lambda from G to A is the Jordan projection, which is the list of eigenvalues. Like in all linear setting, this is the list of eigenvalues.
Do you need the tau on the right?
Sorry, no. Yes.
No, on the right.
On the right, I don't need the tau. I wanted a lot. Thanks. Thank you. Yeah. So I like the point is that I had the root that was like e to the root was giving me some rational function of the eigenvalues. This is an invariant on G, invariant up to conjugation, of G acting on itself by conjugation. And I want this to be read by the first eigenvalue gap in the image. And then we say that for such tau, we say that we denote by omega, which I wanted to be lambda 1 of tau of G. Sorry. Denoted by omega, the associated dominant weight. Where omega is now a function from G to R and satisfies e to the omega of lambda of G is equal to lambda 1 of tau G.
I have a very nice question. Let's say for every root alpha, choose a linear representation, blah, blah, blah.
Yeah.
Is it clear that it exists?
No, it's a fact that exists. It's not uniquely determined by this, and you can choose a minimal one that has this property. For example, let me give an example to be concrete. So, for example, if G is, I don't know, as O PQ, then the possible alpha are log of lambda E over lambda J. So lambda E over lambda I plus lambda E plus 1. Right? I have some eigenvalues. Like I have my matrix in OPQ, I have some eigenvalues. And the roots are all form of like logs of ratios of consecutive eigenvalues. And this is maybe what I call alpha I. And then I can choose as tau I the kth wedge power. So lambda K of R P Q. So this is a vector space whose bases are the K wedge power, the K wedge product of RPQ.
What's RP? P times Q?
RP P plus Q, that's P comma Q. Lambda, sorry, I should call this, maybe I should have this a K, thanks. That's easier to read. So like so this is the basis as, the bases are all the form V1 wedge V2 wedge BK, where VI R and R PQ. Huh?
That's your Rn and not the...
Yeah, that's this tau, tau K is the representation from G to SL of lambda K of RPQ, thanks, which is the natural action. RPQ is my notation for RP plus Q together with the form of signature P comma Q. And that's a choice of the. And this is one example. And of course, and in here, the top, like if you want to get an eigenvector for a matrix, you should choose k distinct eigenvectors. And so the top eigenvalue for this action is lambda 1 times lambda k. And the second eigenvalue is lambda 1, lambda k minus 1, lambda k plus 1. This is the second biggest thing I can multiply with. And the ratio of these two is lambda k over lambda k plus 1.
So you're saying in this example, omega would be lambda 1 to lambda k?
Exactly. In this case, omega of lambda of G is log of lambda 1 up to lambda k. And I'm confused now because maybe I need square. Yeah, no, that's correct, I think.
These are just precise the case fundamental representation. These are precise the case fundamental representation.
Right, these are the fundamental representation. And that was the point. Like, I didn't want to introduce this. These are exactly so the dominant weight, like, they are the top weight for the fundamental representations, just asking that this is the root, doesn't determine it uniquely, because I could take tensor products of this with itself, and then I will still keep the same root, but get the different representation, which have bigger omega. But for what I will need later, I only care that the first root is alpha 1.
For your Jordan projection, is it going into A or A plus?
My Jordan projection is going to go to A plus. And it's the ordered list of eigenvalues in the linear representations.
Excuse me, the domain of omega is A?
Yeah, omega is a linear function on A. Yeah, omega composed lambda. Yeah, thanks. Omega is a linear form from A to R. Yeah, sorry. And these are really the weights Natalie was talking about this morning. So, and the point is that if I do my construction like this, it follows that for any such tau, we have a natural map psi tau that maps my f theta space into f1 big N of n big N minus 1 of Rn, and these actually factors through f alpha iota alpha. So like what this is saying is that there is a standard representation theory that will take more than half an hour to present properly, that is giving me that for any root alpha, I have a representation of my group into SLNR that maps my flag space of interest, or actually the flag space associated to alpha, to be more precise, into the flag space for this SLRN that's composed of a point and a hyperplane, and has this property that's the root, the first root of this representation is the root I wanted, and the first weight of this representation is my fundamental weight that I called omega, that I defined through this representation. Okay. And this lets me construct some families of cross ratios. And then with this, so given a flag manifold f theta and alpha in theta, we construct a cross ratio C and omega, the associated weight, we define the cross ratio omega of x, y, z, t to be the cross ratio that I had up there, which I wrote with which I wrote sometimes with these brackets. So maybe I'll write it CR R Pn of xi tau of x, xi tau of y, xi of z, and xi. Okay, so this has the property again. So this is a map from 4 tuples of points in my flag space to R positive actually, no, to R, that to any 4 points gives me a real number and has the property that it reads the right period. This has the property that this. Sorry. So there's a property that this is an algebraic function on four tuples in this f theta that are transverse, say, pairwise transverse. And there's the property that it reads the periods. So like we have that CR omega of, as before, gamma plus, gamma minus, x, gamma x. This is equal to e to the omega of lambda of gamma. So that if, like, so like the idea is that here at my symmetric space X, I choose an element, an isometry of my symmetric space that had an attractive point gamma plus and repelling point gamma minus in the suitable flag manifold. And now I choose 2 points, again, X. I choose any points in the flag manifold that's transverse to these things. To the pair, so it's a generic property, and I compute the cross ratio on this flag manifold. In which the way in which I compute it is like I take this flag manifold and I put it in RPN cross RPN dual, and I use a standard cross ratio. But what I do is that I read this combination of the eigenvalues that's dictated from alpha in some sort of algebraic terms. And this is, in specific examples, is very concrete. So for example, we're saying here that I take alpha k, the kth root. Let me maybe just do this 1 second. So here I had the SOPQ as a concrete example. I was taking alpha k. I take this representation that's acting on some wedge product of the base vector space. And in this case, the boundary map psi k will land from the isotropic k-dimensional subspaces of what I'm calling RPQ to I was calling this F1 n minus 1 of R of wedge k of RPQ. And this maps X to the kth wedge of X and D minus kth wedge of X. So here, what I mean by this, I have a k-dimensional vector space of X or something. So I start from a k-dimensional vector space. I choose any linearly independent set in here. I get 1 point in the kth wedge power, and vice versa. And this gives me the point in this flag. And the hyperplane is done by saying that I take the orthogonal with respect to the form that was defining here. This is a d minus k dimensional, where d is equal to p plus q. So this is one element in lambda d minus k of R PQ, which is identified with lambda k of R PQ dual. Because if I have a d minus k wedge, I can wedge it with a k wedge and get the determinant, whatever. Like that's linear algebra that you can play with and persuade yourself that it works. Okay, so Yeah.
I'm a bit confused. How do you compute? So, if I'm not mistaken, this C tau of a point gives you a flag.
Yeah.
With a dimension 1 subspace and a codimension 1 subspace.
Right.
How do you compute their cross ratio?
I take the points of the first two and the flag and the hyperplanes of the other two.
Ah, okay. So you project. Okay.
Yeah. I do some further projection. Right? It's just to have one single one boundary map. I could just like think of the flag, 2 points in the flag and 2 points in the dual flag, and just get the representation in the projective space and the dual projective space and compute. There were more questions? Okay. So and this is good because it computes length. And the first theorem that we prove, and I was hoping of telling you a little bit of how we prove, but my times is going much faster than I hoped, is that if I have, if I am in the setting in which I have a theta positive pair, I have a theta positive representation, but this is about really flag spaces admitting diamonds. So if I have 4 points x, y, z, t in f theta to the 4 that are positive, be a positive 4 tuple, so here, when I'm writing this, I'm assuming that I have a g p theta, a theta positive pair. And I have these 4 tuple that in the picture is inside, forms diamonds, x, y, z, t. And there is theta positive 4 tuple, then for any alpha in theta, and for any omega associated to alpha, we have that CR omega of x, y, z, t is bigger than 1. Okay, so now this might seem not so. Why is this interesting? Why I was saying that this is very similar to holonomies of hyperbolization. So let me try to parse this statement for you 1 second. So what I'm saying here is that this is a result that links positivity with these cross ratios that I introduced. But I would say that these cross ratios are interesting because they let you read eigenvalues. Okay? So for the moment, this is just a property of that the positivity in the diamond sense is compatible with the positivity of the cross ratio. So in the circle, for the cross ratio of the circle, so if I have x, y, and t a triple, then having cross ratio bigger than 1 means, so this is in S1, means that my third point lies in this interval. So this z belongs to the red interval if and only if the cross ratio of x, y, z, t is bigger than 1. And in general, I have these cross ratios on flag manifolds that I can use to play, to read eigenvalues and to do constructions similar that I was doing with the projective cross ratio in S1. But this theorem is telling you that this is the positivity forces positivity for this cross ratio. In general, it's more general to have positive, being positive for the cross ratio doesn't imply that you're theta positive, doesn't imply that you have diamonds and that's theta positive, but this is a consequence of this positivity, that all these cross ratios are positive. And why is this interesting? So why is this important? So this property is important because this tells you that there exists, this implies that for that there exists a geodesic current mu omega rho that let me write this and then for any theta positive representation rho from gamma to G that encodes as periods the omega of lambda of rho of G. Okay, so let me tell you. So, like we have seen, like geodesic currents are measures on mu is a Borel measure on boundary of gamma on pairs of points at the boundary of gamma. Geodesic currents appeared in Barbara's mini-course, like the very first lecture, to like another way of reading measure invariant and the geodesic flow for the action of gamma on itself. And geodesic currents are also interesting for another property in Teichmüller theory. So this is one place where geodesic currents appear. The other place is that the geodesic currents also let you read lengths of elements in hyperbolic setting. This is because there is an intersection. So this means that this is the intersection of mu omega rho and delta G. So there is an intersection on all the space of geodesic currents, and this means that any geodesic current has a period that is the length of the element. And having this positive geodesic current that reads this period, this gives you as corollary that if gamma in the fundamental group of SG is not simple, so this is gamma, and I can write it as concatenation of A and B, as a path, then the length of rho of gamma is bigger or equal than the length of rho of A plus the length of rho of B. So one geometric application of having these positive cross ratios, and which I think I can just explain this and say 2 words about how we prove the theorem, is that, I mean, I was saying that like computing this omega of L of gamma is what in the hyperbolic setting was the hyperbolic length. And I can really think of this as some length for the action of my isometry on the symmetric space that I encode on the boundary by looking at the cross ratio. And proving the positivity of this cross ratio for theta positive representation allows me to tell that for those lengths, if I have a curve that's composite of 2 different subpaths, then the length is at least as long as the 2 subpaths.
What was L omega?
Yeah, L omega is omega of lambda of rho of gamma, which is actually equal to the translation length on the symmetric space for some suitable metric that's not the Riemannian metric, that is still G invariant. But the thing that, like, the important thing to keep in mind is that on a topological surface, this is obvious because this is the length is the minimal length of a closed geodesic in the homotopy class, and of course, since this is a concatenation of this, when I cut it out here and let it shrink, it becomes shorter. But if I have more space, as I have in the symmetric space, there is no reason of having an intersection point. And so there is no reason for these to become shorter when you do surgery. And actually, there are lots of examples in which these, I don't know, already in hyperbolic 3 manifolds, where, I mean representation in SL2C, where this does not get shorter as you split it up this way. Because maybe it's really in 3 space, and it's very far up, and this is very long, and so as you cut, it becomes longer, the sum of the two. And so this is a consequence of this theorem that is actually an important part of our work, which I would have hoped of having. Yeah, I get there's sort of like, let me just finish one sentence and then. So, and the idea here is that we reinterpret this cross ratio through a symplectic form on f theta cross f theta that we can understand. I mean, that we can relate to positivity. So we have the question?
Yeah. So my question is, for this corollary, you need the background positive structure, or do you just need that the cross ratios are bigger than 1? What I mean is that if you're only on the limit set,
right?
You had this property.
Guarantee this. Yeah, this is very general. So like for any in any flag space, I have lots of cross ratios. For any Anosov representation, I have a boundary map, and I can use the boundary map to pull back the cross ratio to a cross ratio on the boundary of the group that computes the right periods, that has the right periods. If that cross ratio is positive in the sense that it's bigger than 1, then you have this geodesic current that computes the periods. But the fact that all these theta positive representations have this property is a feature that, to me, makes them very similar to holonomies of hyperbolizations as opposed to other convex compact actions in rank 1. And I think that since my time is up, I'll close it here.
Any question?
So do you even say again what's the punchline of that sentence over there? So why is editable again? I think
yeah, so the punchline is that, so this tells me some properties of this length. So this is relating somehow, so this, I mean, having gamma as a concatenation of 2 loops is something that sees the topology of the group, of the surface. Because I want that, like, I have this crossing picture that's not just like that this is a concatenation of 2, like it's not just an abstract writing in the fundamental group, but it's something that sees the topology. Because otherwise, if I write in words, it's not clear how to split this up. And what I'm doing here is that I'm taking the smallest translation, the stable length, or the smallest translation distance of this word that in the surface was concatenation of 2 loops passing from 1 point. And I know that this is longer than the other 2. In general, this is very false. For many representations, it is very false. And in general, so this is true in surfaces because I have a 2-dimensional picture. And so I can cut, like I have this intersection, like in the surface, I can see that this loop self-intersects. And so in the surface, I can cut it out through this point. Already, if you give a little bit more room in acting on H3, this is not going to be true anymore. And if this does not self-intersect, when you do A, you have to add, like you think of this as projecting down, you have to add this segment in between. And so the sum of this length plus the sum of that length has this extra piece that can make it longer. Yeah? And so this is telling you that your theta positive representation, or in general, representation for which such cross ratio is positive, see a lot of the topology of the surface, of the underlying surface, and not the abstract fundamental group. Okay. Maybe another point that I could make here is that all this theory works the same for free groups. And free groups are fundamental groups of surfaces in different ways. And the theta positive representation, see in which way your free group, like for example, a free group with two generators, is fundamental group of the surface of the pair of pants and of the once punctured torus. But the self-intersection will depend on the surface that you choose. And your theta positive representations will remember this.
So is it good enough to have a conclusion about cross ratios of your theorem to derive that? I mean, is it good enough for this corollary to have a cross ratio bigger than 1?
Yeah,
because that property is more general than positivity.
Exactly, yeah. So there are many classes of representations that are not theta positive, for which on the whole boundary of the group, like as a subset of the flag space, this cross ratio is positive. If that happens, then you get this corollary. But maybe just as a side remark, like 10 years ago, I was very allergic to geodesic currents, and I did not want to have geodesic currents. And for maximal representation, I tried very hard to prove this thing by hand, doing linear algebra, and I never managed. While with geodesic currents, it's just like very, very easy. So.
Last question.
And maximal representation fit the bill?
Right. Yeah, maximal representations are one of that family up there. So are theta positive with respect to the action on the Shilov boundary. And in that case, this is one of the exercises. In that case, once you understand what this cross ratio is and what's the theta positive structure, it's very easy to show this positivity. It comes basically from the way this is defined. And but just having this positivity, it's very hard from there to deduce such a corollary, while through geodesic currents, it's very easy.
Is omega uniquely associated to alpha or?
No, I mean,
okay.
Yeah. So like the point is really that what we need for this result, any combination, like I mean for any alpha with some more Lie theory, you can see that any alpha is associated to one fundamental weight, and these the fundamental weights that are one per root span the weight lattice. And what is true more generally is that for any weight that is generated by the fundamental weights associated to elements in theta, you have an associated cross ratio the same way, and this associated cross ratio will be positive.
Let's so we can get to the coffee break, because I think our last speaker has a train to catch. More questions during coffee. We'll have coffee, but thank you. We appreciate it.